Hi, okay. Good afternoon. So this is the continuation of our lesson last week. So last week we have tackled about the derivation of equations starting from linear quadratic equations down to complex equations. And also we have uh, we had an introduction with springs. We have discussed springs in equilibrium in relation with springs in unloaded position or static position. So today, konting refresher lang, papakita ko lang sa inyo yung relation ng static position ng springs down to springs with added forces in it. So, ito, yung springs natin, let's say, wala pa siyang load. Okay? And I just want to see, let's consider the position of a spring attached with a block with weight M. Okay? As you can see, our spring have been stretched to a certain elongation. So from this position down to this position, we have the elongation delta. You could call it delta. And such that, nilagyan natin siya ng load wherein acceleration is equal to 0. Nilagyan natin siya ng load ng very, very slow such that acceleration would be 0. And now, yung magiging topic natin is the spring in acceleration, okay? And also, the force acting on it. Meron na siyang mass, and also, hinila pa natin siya pababa, or let's say, acceleration would be equal to the second derivative of x. Now, I'll be making the free body diagram of this block, position 1, okay? Sabi ko. At position 1, we have the free body diagram. Of course, ang weight natin would be equal to mass times gravity, and yung spring, yung force from the spring, which we could call K times delta. So, yung K is the constant of the spring, call it spring constant, times the delta or the change in position. At sabi nila, di ba, the summation of forces acting on a diagram in equilibrium is equal to 0. By this, we have K times delta minus mg is equal to 0. Or we could equate mg to k delta. Correct? Ayan. Now, moving on to the second position. wherein the spring is subjected to acceleration. So, at position 2, para ma-appreciate nyo yung body diagram natin, we still have our mass times gravity and also yung tensile force natin from the spring, but we will equate this to the constant times delta plus x, or this is the summation of the elongation from the equilibrium down to its second position. So this is delta plus x. I hope it makes sense, okay? Delta plus x. Okay. So, again, the summation of forces acting on our body would be equal to mass times gravity minus k times delta plus x. If we will expand this, you would get mass times gravity minus k delta plus, or I mean minus kx. And as you could see, since the forces acting on the body in acceleration is equal to mass times acceleration, we could equate this to mass times acceleration. Also, looking back at this equation, mass times acceleration is equal to mass times gravity minus mass times gravity minus kx. So we could cancel out mass and gravity, and then mass times acceleration would be equal to negative kx. Sabi din natin kanina, acceleration is equal to the second derivative of x. Now, if itatranspose natin yung mass times sa kabila, dun sa kabila, tayo, mass times the second derivative of x equals to negative kx. Kapag tinranspose natin yung m, second derivative of x would be equal to negative k times x over m. Okay, so kagaya ng pagde-derive natin noon, by extracting the roots of our x, kakameron tayo ng, sorry, m squared is equal to negative k over m. Now, transposing the square root, m is equal to negative km m. We have the roots m is equal to positive negative square root of k over m times I. Therefore, kung meron tayong complex roots, we could represent this to an equation which is x c1 cosine yung ating k over m times t plus c2 sine k over m times t, so on and so forth.